we're going to change gears from some things that we've been doing lately and deal with some numbers that you may not have seen before. So this is section 3.1, the I can statement, is I can classify different types of numbers. So let's write the word numbers right there. And the warm-up, we're going to talk about some numbers that you may be aware of already. So warm-up A, it says list as many different types of numbers as you can think of. So for example, whole numbers, fractions, different things like that. I'll give you just a second to think about that. You can pause the video if you want, but think about different types of numbers. How do we classify numbers? So you may have thought of things like this. Well, we know there's a difference between negative numbers, positive numbers. So negatives and positives. We mentioned fractions right here. I gave you that hint. We're also aware of, and we've worked with decimal numbers. Maybe 0 is a number that you're familiar with. And also we've talked about mixed numbers and improper fractions. All sorts of things like that. So improper fractions. So there are tons of different numbers, and you may have thought of different numbers than what I've written down there, and that's totally okay. The next warm-up question is, what is the root word of the word rational? And the root word of the word rational is right here. The root word is the word ratio. Okay, and when we're talking about a ratio, you may remember that we can write down a ratio several different ways. Usually, you're not going to see it with the colon right there, or sometimes we might write it with the word to. Those aren't used very often. What we usually do is we usually write it as a fraction. Okay, so this is a ratio of 1 to 2, this is a ratio of 1 to 2, and that's a ratio of 1 to 2. So when we're talking about rational numbers, what we're talking about is fractions, or numbers that can be written as fractions. And then the last part here, it says if you had to describe what a number is, what would you say? And then be prepared to be called on in class. So if you're listening to a live lecture here, you'd want to be on your toes and be ready to describe what a number is. So a number, probably a good way to describe this is it's a symbol. So it's a symbol, and what it does is it represents a quantity. That represents a quantity, Quantity, quantity. Or in other words, how much of something there is. How much, whoops, we'll do this, how much there is. So whether we're counting sticks or animals or whatever it happens to be, it's a symbol that represents how much of something that there is. So my next question is, are Lego sets different than a set of Mega Bloks? Now you may or may not have played with both types of these. I'm going to show you a picture of these in just a second, but this is going to lead into how we're going to classify numbers. Numbers are very similar to each other, but we can categorize them. So I'm going to show you that there is a difference. Okay, so the answer on this is yes, and I'm going to show you why. I've got a picture right here that I pulled off the internet. These are Mega Bloks, and these are Legos right here. This one does look a little bit bigger in the image. They are actually the same size. They're the same size, the same shape and everything, but Legos are just a little bit better. They're kind of a more high quality construction and different things like that. They're usually expensive, and Mega Bloks are usually a little bit cheaper. Where Legos maybe fit together perfectly and they're really tight and stuff like that, Mega Bloks maybe are a little bit looser and stuff like that. So they are a little bit different, and you could kind of tell, we could kind of say, well, this yellow one is very much like this yellow one over here, but this one has solid tops and this one has little holes right there. So they are slightly different, but they're very similar. They have a lot of similar properties. So we're going to go back and we're going to take a look right here. We mentioned some of the ways that we can tell, and now we're going to talk about sets of numbers. So all the numbers that you're aware of can be classified, and when we say classified, what we mean is we can group them into different sets of numbers. Just like sets of Legos or sets of Mega Bloks, we can make sets of numbers, and each set has its own characteristics and properties. So some of the numbers that we're going to need to understand and remember are the following. So the first one are the natural numbers, and sometimes people call these the counting numbers. These are the very first numbers that you came across. So they're like the numbers 1, 2, 3, 4, and I'm going to put a dot, 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 so that continues. So the natural numbers, if you ever hear anybody talk about that, they're just talking about the counting numbers. We count starting at 1, 2, 3, 4, and so forth. And then there are the whole numbers. Those are the natural numbers. So it's this entire group of numbers right here, including the number 0. And you may not realize this, but 0 is actually a very sophisticated idea or topic. We kind of take it for granted, but it took people a long time to figure out how to deal with 0. So if we're talking about the whole numbers, we're talking about that same list, 0, 1, 2, 3, 4, and so forth. It just starts at 0. And then you're well aware of the integers. I've got an asterisk by that because that's really important. Well, the integers are the positive and negative whole numbers, including 0. A lot of people forget to throw 0 in there. One way that you could say that is it's just the whole numbers and their opposites. So the opposite of 1 would be -1, and the opposite of 2 would be -2, and so forth. Okay, this kind of describes everything in nice plain terms. So integers are the positive and negative whole numbers, including 0. So I'm going to put a ... and then I'm going to do -4, -3, -2, -1. 0, of course, is right in the middle. It doesn't have a sign. And then we can continue on in this direction right here. Those are the integers. Okay. Now, when we talk about rational numbers, we talked about that root word before. So the root word is rational. So these are numbers that can be written as a ratio. I'm going to use the word ratio. A ratio of two integers. So we've got an integer on the top and an integer on the bottom. So I gave you an example earlier, so it's the number 1/2. Or we could have a negative, so we could have -3/4 or something like that. Those would both be integers. And if you take a look at what I've written down here, those are really just fractions. So when we talk about rational numbers, I'd like you to think of the word fraction. When somebody says, hey, we're going to deal with rational numbers, then they're talking about dealing with fractions, or numbers that can be written as fractions. So let me give you an example right now of something like that. So let's say 0.25. Well, 0.25 is the same as 1/4. It can be written as a fraction. In fact, if we've got any number that has a terminating decimal or a repeating pattern, and we're going to see this in the next couple days, but if I write down something like this, 9.63, that is, let's see, what would we have here? 963 hundredths. 963 hundredths. Okay, so we could take that decimal and we could write it as a fraction. We could also take numbers like the number 2. 2 is a fraction. We could put it over 1. In fact, 0 is also a rational number because we could put that over 1, and same for -7 and things like that. So if I were to write something like 15.0, we could just put that over 1, take off the 0, and we've got a rational number. So decimals that terminate, in other words, if they stop or have a repeating pattern, those are rational. Those are also rational numbers. Now, if we take a look at this this list that we've talked about so far, that pretty much covers every type of number that you've ever seen. Now, there is another type of number. So if rational numbers are the numbers that can be written as a ratio of two integers, if we can't write a number as a ratio of two integers, then it's called an irrational number. So an irrational number, they're numbers that cannot be written as a ratio of two integers. Now, these are pretty interesting numbers. We don't encounter them very often, and it'll be a while before you see them on a regular basis, but we are going to see some irrational numbers in this particular unit. So irrational numbers are decimals that go on forever and never have a repeating pattern. So they'll always go on forever, but they will never have a repeating pattern. So some examples would be the number pi. The number pi is 3.14159, and then a whole bunch of decimals that go on forever but never repeat. The number e, and you'll run into that in a couple of years, that's called the natural number. And e is 2.71812, I believe, blah, blah, blah. A whole bunch of stuff, but it never repeats, and it just goes on forever. So what we're going to run into a lot in this unit is square roots and cube roots. They look like this. So this weird radical symbol right here. So these are square roots and cube roots. Okay, now you may have heard of these before, or you may not have, but that's what we're going to go over in this particular unit. So don't be afraid if you haven't seen these before. Most square roots and most cube roots, they are irrational. You can't write them as a fraction. and they're big, long, ugly decimals that go on forever and never repeat. So if we put all of those together, then we get what we call the real numbers. So the real numbers are all of the irrational numbers, every single one of those really ugly numbers like these guys right here, and the rational numbers. So all of those fairly nice numbers that we were talking about up here. So all of these nice numbers up here that can be written as a fraction. So it's all of the irrational numbers and all of the rational numbers together in one big gigantic set. Okay, so if we gave some examples of real numbers, it really would be every number you have ever worked with. Every number you have ever worked with is a real number. You won't be able to, at this point, at your age and with the math that you've been exposed to, think of a number that is not a real number. So I've got a diagram right here, and we'll run through and we'll take a look at this. So this big box right on the outside right here, these are the real numbers. Okay, so every number you can think of so far, that's a real number. And then I'm going to put the irrational numbers over here. So irrational goes over here and rational goes over here. And the thing I want you to notice is there's no overlap. This box right here and this box right here do not overlap. So this one right here, these are numbers like pi. These are numbers like the cube root of 5, the square root of 2, and numbers like 0.9234, blah, 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 and it goes on forever and it never repeats. Okay, so kind of ugly numbers right there. Rational numbers would be things that can be written as a fraction, so they would be things like the fraction 1/4 or 0.25, the number 5, the number 7, the number -2. Again, even ugly things like what we had up above, 9.63. Anything like that would be totally okay. And even numbers like this, 0.3 repeated, because that's going to be 0.33333. It's going to go on forever, but it's got that repeating pattern there. Okay, if we narrow in just a little bit and kind of exclude numbers that can just be written as fractions, let's talk about some really nice numbers. The integers, they are a smaller set of numbers that are contained inside the rational. So those are those -2, ... -2, -1, 0, 1, 2, and then continuing on. And then we've got the whole numbers here. That's 0, 1, 2, 3, and so forth. And then the smallest set that we're going to talk about at all, those are called the natural numbers, and those start out at 1, 2, 3. Again, those are just the counting numbers right there. Okay? Now, this takes a while to kind of digest, but keep this in mind. We're not going to talk about every single one of these sets of numbers and classify those, but you do need to be aware of that every number that we've dealt with so far, we can call that a real number, and then we break it into two completely separate groups. The irrational numbers over here, these are pretty ugly numbers to work with, and then we've got the rational numbers here that, you know, maybe a decimal or fraction isn't your favorite, but some of these definitely are. These are really nice numbers like the integers, the whole numbers, and the natural numbers. Whoops. Let's see, I spelled that wrong, didn't I? Natural. Okay, we'll get that right there. Okay. All right, so we're going to flip this down here. And again, just keep in mind, it's very important to note that a number can belong to more than one set of numbers. So for example, if a number is rational, then it's automatically real. If a number is natural, then it's automatically in this group of whole numbers. It's automatically in the group of integers and rational numbers and real and so forth. And even for over here where we've got an irrational number, it also qualifies as a real number. So what we're going to do is we're going to work on classifying these numbers, but not in all of the groups. We're only going to worry about whether or not it's an integer, a rational number, an irrational number, or a real number. That's all we're going to concern ourselves with for the time being. So this next little bullet point right here says, all of the numbers that you have ever used or will use for the next few years are all real numbers. Okay, so just a reminder of that. Everything that we're going to deal with this year and probably for the next little while, they're all real numbers. And a number can a number be both rational and irrational at the same time? Well, remember, let's take a look at this right here. We're talking about irrational numbers and rational numbers right here. And the question is, can it be both of those at the same time? It's either got to be in this group or in this group. So the answer to that one right there is no. It's got to be one or the other. It can't be both rational and irrational. Okay? So this one says circle all the sets to which each number belongs. Now this is very similar to what your assignment is. All you're going to need to do is go through here and look at this and say, okay, what is this for sure? And we'll circle those. So is this an integer? Is it a positive or negative whole number including 0? Well, the answer to that is no, so we're going to leave that alone. Is it rational? Remember, when somebody says the word rational, you're going to think fraction. Well, gosh, that's written as a fraction, so we're in good shape there. Is it irrational? Well, remember what we said just above. If it's rational, it can't be irrational. So it's not going to be irrational, but remember, every number that we're going to run across is going to be a real number. So we can go ahead and circle that one. Let's take a look at the next one. Take a look at B. This is 0.243 with a bar over the 43, so that 43 is going to repeat. It's going to be 2.434343. So that's definitely not a positive or negative whole number, so it's not going to be an integer. Because it's got a repeating pattern, it is rational, which means it can't be irrational, and every number on here is going to be real. So let's go ahead and do this. Every single one of them is a real number. Okay? Some of these look really weird, but these are all real numbers. Okay, let's take a look at this one. This is the square root of 2. This is can be turned into a decimal. It goes on forever and has no repeating pattern. Definitely not a whole number, positive or negative. It can't be written as a fraction, so that one's going to be irrational. We've got a negative whole number, so that's going to be an integer. Remember, we could write that as a fraction. We could put it over 1, so that's going to be irrational, which means it can't be irrational. And again, we already took care of the real part on all of these. So let's take a look at this one right here. Now, you might draw your eye to both of these right here. They're both very similar, and there is a difference between the two of these. They're exactly the same decimal number, but this one goes on forever, and this one stops. If this one stops, now neither of these are an integer for sure. If this one stops, that means it's rational. If this one goes on forever, and notice there's no repeating pattern, this one has to be irrational. Let's see, negative 9.56. That one is a terminating decimal, so we could write that as a fraction if we needed to. So it's definitely rational. And again, notice how we're hopping back and forth here. If it's in one of these categories, it can't be in the other. There's no way that's an integer. It's not a whole number. Let's see, take a look at 0. 0 is an integer. It can be written as a fraction, so it's definitely a rational number. It means it can't be irrational. And then we've got this one right here. Now notice this is written as a ratio, so it's definitely rational. It's not irrational, but let's check and see if it's an integer. This one has an asterisk by it for a reason. 4 goes into 84. It goes in there 21 times. So this is actually negative 21. And negative 21, if we reduce that and simplify it, it's definitely an integer. So we've got that one taken care of. This is what your assignment's like. I do want to kind of challenge you to go back every once in a while and review things that we've learned. These are going to come up again every so often on assignments, maybe even on tests or bonus questions or different things like that. So make sure you're aware of these. So the stuff up above in the table, that's what your assignment is like, but I'm hoping you remember how to do this right here. So we've got a variable on both sides. I'm going to subtract 9r from here and 9r from there, and look what happens. Do you know what to write down for an answer on that? Negative 9 does not equal negative 6, so we would write no solution on that one. And let's take a look at this one. I'm going to do the same thing here. I'm going to subtract 3x from both sides. And again, notice that the variable goes away and I end up with 4 equals 4. 4 always equals 4. There's nothing we can do to mess that up. That means we could plug in anything we want. So we would write infinitely many solutions on that particular problem. Okay, good luck with your assignment. It looks very much like this guy right here.